Welcome back to the deep dive. Today we are jumping into a really fascinating piece of physics history and theory. It's all contained in chapter 41 of Feynman's lectures, Vol.1. The title is The Brownian Movement. Now, you might hear Brownian motion and just think, oh yeah, pollen grains jiggling in water. A bit of trivia, maybe, but that's really missing the incredible story Feynman tells here. This chapter, it's a masterclass. It takes this seemingly random, chaotic jiggling.
Yeah, this messy little phenomenon.
Exactly, and uses it as a lens to look at, well, almost everything. Classical mechanics, heat, thermal energy, and even the exact point where classical physics just broke.
Right, where it failed spectacularly, leading to quantum mechanics.
So our mission for you today is to follow that intellectual thread. How does this tiny random movement connect to fundamental ideas like the kinetic theory of heat? How does it expose this deep flaw in 19th century physics? And maybe most amazingly, how does watching a speck of dirt jiggle let us figure out the size of an atom? It all hinges on one quantity, kilophtiges.
Kilodolars? Yeah, that's the characteristic thermal energy. And what Feynman does so brilliantly here is show how this kilodollar connects seemingly disparate things. We start with particles bumping around, then we move to electrical noise and wires, and then even to the color of light emitted by hot objects. It's all linked by kilodollars and this idea of equilibrium.
Finding patterns in the chaos.
That's a great way to put it. Deep, quantifiable patterns.
Okay, so let's start where Feynman does with the history. Robert Brown, 1827, he's a botanist, right?
Yep, looking at pollen under a microscope.
And he sees these grains suspended in water just constantly moving, jiggling erratically nonstop.
The first thought was, maybe they're alive. Some kind of microscopic life force.
But no, it turned out anything small enough did this. Dust, soot, whatever. It wasn't life.
The real cause, as we now know, was the water molecules themselves. Tiny, invisible, constantly smashing into the larger pollen grain from all sides.
And this observation, this Brownian motion, became the first sort of visible proof of the kinetic theory of heat, didn't it?
Absolutely.
Oh.
It showed directly that these suspended particles, once they reach thermal equilibrium with the fluid, meaning they're at the same temperature dollars, they must have the same average kinetic energy as the fluid molecules hitting them.
Which brings us straight to the equipartition theorem. This is a really core concept here.
It is. It's elegant, really.
The idea is that for every way a particle can move or store energy, what we call a degree of freedom.
Like moving along the x-axis or the y or the z.
Right. For each of those, the average kinetic energy associated with that motion is exactly 1/2 kilodollars.
Exactly, for equinocutidol. So for a particle free to move in 3 dimensions, the total average kinetic energy is $1/kilokutidollar.
Feynman uses this great thought experiment to make it intuitive. Imagine you have a box of gas, tiny light molecules zipping around fast.
Like an ideal gas.
But mixed in with them are these huge, heavy pellets, like millions of times heavier than the gas molecule.
Or big, slow things.
Yeah, you seal the box, wait for everything to reach the same temperature, $2. Now, what's the average kinetic energy of those massive, slow-moving pellets?
Well, your first instinct might be that they'd be much colder, have less energy, they're getting knocked around by tiny things.
Right. But the equipartition theorem insists, no, their average kinetic energy must also be fract 2 kTs, same as the little guys.
But how? I mean, wouldn't friction or drag from the fluid just slow those big pellets right down, transfer their energy away?
See, that's the crucial point about equilibrium. Yes, drag tries to slow the particle down.
But the molecular bombardment never stops. Those random kicks from the fluid molecules keep pumping energy back in.
So the drag slows it, the kicks speed it up, and in equilibrium, they balance out.
Precisely. The pellet moves much slower, sure, but its mass is much larger. So the average frac 1 angle V2 Yogi still comes out to frac ID. Thermal equilibrium demands this energy sharing, regardless of the particle size. It's quite profound.
Okay, so kVolars is this fundamental energy scale set by temperature. It governs particles. Where else does it show up? You mentioned electrical systems.
Yeah, we could take this exact same principle and apply it to things that aren't just physical particles moving around. Think about oscillations.
Like a pendulum?
Sort of, yeah. Or even better, think about a really sensitive measuring device, like a galvanometer mirror. It's a tiny mirror hanging on a very fine wire or fiber.
Used to detect tiny electrical currents, right? The current makes the mirror twist slightly.
Exactly. Now, that mirror on its fiber is an oscillator. It can twist back and forth, and it's sitting there in the air at room temperature, $2.
So it's in thermal equilibrium with the air molecules.
Which means it's constantly getting bombarded by them, just like the pollen grain.
So the mirror itself must be exhibiting Brownian motion.
Absolutely. Its rotational motion will have an average kinetic energy of fret kd dollar, and because it's twisting a fiber, it also has potential energy stored in the twist, which also averages fret k dollar.
So the total average energy of this tiny oscillator is just k to dollar.
Just k to dollars. If you shine a beam of light off that mirror onto a wall, the spot of light will never be perfectly still. It'll shimmer and wobble constantly because of those cadal kicks from the air molecules.
That's amazing. The same k to dollar is causing pollen to dance makes a mirror shimmer. And this connects to electrical noise.
Directly. Think about a simple resistor. What is it? It's a material with atoms and electrons inside.
Okay.
Those electrons aren't stationary. They're part of a system at temperature dollars. So they must be jiggling around randomly due to thermal energy.
The electrons themselves have k to dollar energy.
They participate in the thermal equilibrium, yes. And moving electrons are an electrical current, a random jiggling current.
Which means a random jiggling voltage across the resistor.
Exactly. That's Johnson noise or thermal noise. It's the electrical equivalent of Brownian motion. Any resistor, just by virtue of being at a temperature dollar, generates this unavoidable random voltage noise.
And the amount of noise power it can deliver
is directly related to cadal dollars. And interestingly, when you look at the maximum power you can get out, it doesn't even depend on the value of the resistance itself. It's fundamentally set by cadal dollars.
Wow, okay, so cadal dollar governs particle motion, mirror oscillations, and electrical noise. What about light? You mentioned black body radiation.
Right. This is where applying the idea of cadal dollars led to a huge crisis in physics. The setup is a black body cavity, basically a sealed box, perfectly absorbing, held at a constant temperature, $2.
Inside this box, you have electromagnetic radiation light waves bouncing around, and maybe you place an oscillator, like our mirror, or even just an electron that can wiggle inside the box too.
In thermal equilibrium, that oscillator must be exchanging energy with the light waves. It absorbs light, it emits light.
And classically, following the equipartition theorem,
the average energy of that oscillator should be cadal dollars. So the reasoning went, the amount of light energy at any given frequency inside that box should somehow be proportional to kilodollar.
Makes sense based on everything we've said so far. So what was the problem?
The problem came when physicists like Rayleigh-Jeans actually calculated the implications of this for the light waves themselves.
Oh.
They treated each possible frequency or mode of light wave inside the cavity as an independent oscillator that should, on average, contain kilodollar energy.
Okay.
But there's no limit to how high the frequency of a light wave can be. You can have incredibly high frequencies, ultraviolet, X-rays, gamma rays, infinitely many possible modes.
So if each mode has kilodollar energy,
Yeah.
and there are infinite modes,
You get infinite energy. The classical prediction, the Rayleigh-Jeans law, said the intensity of the radiation should just keep increasing forever as the frequency gets higher, an infinite amount of energy packed into the high frequencies.
that's clearly wrong. Hot objects don't emit infinite energy.
Not even close. This is the ultraviolet catastrophe. It was a complete breakdown of classical physics when applied to light and heat. The experimental measurements of blackbody radiation showed something totally different.
What did they show?
The actual spectrum, the intensity of light at different frequencies. It starts low, rises to a peak at some frequency that depends on the temperature, and then it falls off rapidly at higher frequencies. No infinity in sight.
So the equipartition theorem, which worked perfectly for pollen grains and resistors, just completely failed for light waves inside a hot box.
Spectacularly failed at high frequencies. It worked okay for low frequencies, but was disastrously wrong for high ones. Physics was fundamentally broken.
Which forced Max Planck to come up with, well, a hack, almost.
It started as a mathematical trick, yeah. He found he could match the experimental curve perfectly if he made a radical assumption that the energy of the oscillators exchanging energy with the light field couldn't be just any value.
Not continuous.
Not continuous. He proposed energy comes in discrete packets or quanta. The energy of an oscillator could only be 0, or bar omega, or $2 bar omega, and so on. Integer multiples of a fundamental energy unit bar omega, where the mega is the frequency and the bar is this new tiny constant, Planck's constant.
Energy is quantized. Little jumps, not a smooth ramp. That's revolutionary.
Absolutely game-changing. And when you recalculate the average energy of such a quantum oscillator using statistical mechanics, you no longer get the simple particle dollars.
You get that more complicated formula.
Right, the one involving the bar omega divided by side raised to the power of the bar omega t minus 1.
And the magic of that formula
is that when the frequency in omega gets very high, the energy quantum omega t becomes much larger than the typical thermal energy kilodollars.
Okay.
When that happens, the exponential term E omega gets huge, and the average energy plummets towards 0.
Ah, so the quantization naturally suppresses the energy in those high-frequency modes.
Exactly. It chokes off the ultraviolet catastrophe and makes the predicted curve perfectly match the experiments.
So the failure of classical key dollars for light directly led to the birth of quantum mechanics.
That's the story. The equipartition theorem, k-bar dollar, only holds when the energy quanta bar omega are small compared to the thermal energy k-bar dollar. Trying to understand thermal equilibrium noise, heat radiation forced physics into the quantum age.
Incredible. Okay, let's bring this full circle. We started with the physical jiggling. How do we actually analyze that motion mathematically? This brings us to the random walk.
Right, the random walk is the mathematical model we use to describe processes like Brownian motion. Imagine a particle starting at the origin.
Okay.
It takes a step of a certain length, say all dollars, in a completely random direction. Then another step, length relative random direction, then another and another for another steps.
Where does it end up?
Well, because the directions are random, on average, its final position is still right back at the origin. The average displacement is 0.
Seems like it hasn't gone anywhere then.
But that's the average vector position. What's more interesting is the distance it travels from the origin.
Yeah.
We look at the mean square of the distance, R2 wrangle.
Okay, the average square distance.
And it turns out, mathematically, that Langle R2 wrangle is proportional to the number of steps.
Nah, so the more steps, the further away it tends to get squared.
Exactly. And since the number of steps is usually proportional to the time elapsed, we find that the mean square distance is proportional to time. Langle R2 wrangle, propto T.
Which means the typical distance traveled, the root mean square distance, grows like the square root of time, not linearly with time.
That square root dependence is key for diffusion processes. Now, we apply this model to the real Brownian particle in a fluid.
It's getting kicked randomly by molecules, the steps.
But it's also experiencing that continuous drag force from the fluid, which we characterize with a drag coefficient, usually called Duchek.
So it's a competition again. Random kicks trying to make it diffuse outwards according to square and drag trying to slow it down.
Precisely. And Feynman shows the derivation where these effects are balanced. You consider the forces, relate them back to the t-key-dollar energy scale.
And what comes out?
You get a beautiful, powerful equation that connects the measurable macroscopic diffusion to the microscopic thermal energy. It relates the mean square distance Langle R2 wrangle over time to the temperature tolerance and the drag mu.
The specific formula.
For 3 dimensions, it's Langle R2 wrangle, 6 Ka frac mu.
Okay, Langle R2 wrangle, 6 TT mu. And this is huge because...
Because we can measure everything on the right side except color.
Wait, really? How?
Well, you can watch the particle under a microscope. You measure how far it diffuses, squared all Langle R2 wrangle over a certain time dollars. That's doable.
Okay.
And you can measure the drag coefficient medial for that same particle, maybe by seeing how fast it settles under gravity in the fluid. That's a macroscopic measurement, the temperature dollars.
So you have Langle R2 wrangle over dollar. The only unknown is color, Boltzmann's constant.
Exactly. By observing the random walk of a tiny particle, you can experimentally determine the value of dollars. This was first done rigorously by Jean Perrin around 1908.
And once you know the color,
the game changes. Because we already knew the ideal gas constant, $20, from macroscopic gas measurements. And the fundamental relationship is the dollars equals K and Ni, where U allows Avogadro's number.
the number of atoms or molecules in a mole.
Right, so by measuring dollars from Brownian motion, Perrin could calculate Avogadro's number. He could effectively count atoms by watching dust motes dance. It was undeniable proof of the existence and scale of atoms and molecules.
That is just incredible, all from that random jiggling.
It's a stunning synthesis.
Okay, let's try to recap the journey here. We saw Brownian motion itself, giving visible proof for kinetic theory and leading to the equipartition theorem, defining the role of whirlers in physical motion.
Then we saw dollars applied to oscillators, leading to Johnson noise in electronics, and crucially to the black body radiation problem.
Which broke classical physics and forced the invention of quantum theory.
Right. And finally, the random walk model provided the mathematical tool to analyze the actual Brownian motion quantitatively,
allowing us to measure dollars and ultimately determine Avogadro's number, none dollars, proving the reality of atoms.
That's the arc, all connected by thermal equilibrium and dollars.
So for you, the listener, the takeaway is just how fundamental this thermal energy scale dollars is. It's not just about temperature. It dictates the energy landscape for everything from molecular collisions to electrical noise to the very nature of light.
And maybe a final thought to leave you with. Consider that the simple, unavoidable fact that a tiny mirror reflecting a light beam can't stay perfectly still. that its thermal jiggling dictated by Kettigall refused to follow the old rules when applied to light itself. That microscopic wobble is what ultimately unraveled all of classical physics and launched the quantum revolution. Thermal equilibrium is a surprisingly powerful and sensitive concept.
A fantastic journey through a single pivotal chapter. Thanks for joining us on this deep dive. We'll see you next time.